Hi, my name is Chris Kempes. I'm from the Santa Fe Institute. And today I'm going to talk about the role that statistical frameworks and theory in general can and already do play in life detection. To give you a brief overview, first I'm going to talk a little bit about Bayesian methods in astrobiology, point out some general challenges, and then talk a bit about the need for new types of theories of life for life detection. The role that Bayesian methods can play in astrobiology is something that has recently started to take off in the field. And here are two really nice papers discussing at both a very abstract and general level and a more specific level how different types of Bayesian methods might be used for life detection. And so since this is becoming a tool that will likely be deployed in lots of different scenarios, I want to give you first a sense of how Bayesian statistical inference works. So it all relies on this very simple premise of Bayes' theorem, which says that the probability of a particular model given a set of observations, given some set of data, is this simple ratio of the probability of that data given a model times the probability of that model divided by the probability of the data. Now, this is the simplest way to write down this formula. It's not necessarily the easiest way. And so what people typically do is rewrite this Bayes formula in the slightly more illustrative way, where you've broken up the probability of the data in the denominator into this probability of the data given the model again, times the probability of the model, plus this probability of not observing that data or observing that data under not the model. So thinking about all other alternative models to the one you're considering and asking how likely those are to produce the data. Now, the two key features that go into this are this prior probability of observing a particular model, that's P of M, and this thing that's known as the likelihood ratio, which is the ratio of the probability of the data being observed under all other models that are not the one that you're interested in, divided by the probability of seeing the data under the model that you're considering. And so if we write this in terms of a life detection problem, these are typically the formulas that people write down. So in this Walker et al. Paper, you can see very explicitly the probability of the probability that you have life given the data equals this same sort of breakdown, where you can see that there's a probability of data under the model of life and probability under the data, the probability of the data under a model of no life. And so this is typically how you would start to formulate a problem. But one of the ways that Bayesian inference is sort of most immediately useful is in thinking about comparing two competing models. And this is often how it gets used in various fields. And so the idea is, imagine I have two models I'm interested in, model 1 and model 2. I can write down each in this Bayesian way. And then I could ask myself, what's the ratio of the likelihood of model 1 under the data compared to model 2 under the data? And when I do that, this probability of the data totally drops out from the formula, which is nice. And I'm left with this ratio of probability of the data under model 1 over probability of data under model 2, each multiplied by these two different prior probabilities. Now, if I have a case where I really have no sense of the prior probabilities, or where they're approximately equal, I can reduce this equation to just this ratio of the probability of the data under model 1 versus the probability of the data under model 2. And so this is now in a simple way where I simply have to have a way to take a model and use it to generate a set of data. And if I have two different models, I can start to compete them against each other, which is really useful. Now, this can become very complicated very quickly in lots of different statistical or machine learning or abstract scenarios. And so I want to give you just a very simple test case that's sort of the textbook example to give you a sense of how this gets used and what the procedure actually looks like. And so that example is, imagine if you have a coin and you're just trying to test whether that coin is a fair coin or not a fair coin. And you throw it 10 times, so you toss it 10 times, and you observe 8 heads. And the question is, given this observation of 8 heads out of 10 tosses, how likely is it that this is a fair coin? What's nice is in this scenario, we have an explicit model of probability based on how biased the coin is. And so what we're looking at then is the probability of 8 heads given our model for how biased the coin is, which is represented by this little parameter b. In this case, we can write that down as an explicit theoretical equation because we understand the combinatorics of this problem. And once we do that, we can then compare 2 different biases against each other and ask how likely one model is against the other. So in this case, I'm comparing the bias of a coin that has a 0.8 bias versus a coin that has a 0.5 bias. And you would see here that this likelihood ratio is close to 7. So what that says is that it's 7 times more likely that the bias of this coin is 0.8 than it being fair at 0.5. So it's 7 times more likely to have a bias of 0.8 than being a fair coin. And even if we looked at the coin just being slightly not fair, so having a bias of 0.55 against 0.5, we see that it's twice as likely for this coin to have a slight bias of 0.55 opposed to no bias at all. And so it's this sort of model competition or model comparison that where I think is often a Bayesian framework is most useful, because you can say we have 2 theories, we want to compete them against each other and say something about the data that we're seeing. And this sort of idea has been put to use very recently in this paper looking at data from the Cassini probe around Enceladus, where the basic idea here is to say, let's take observations of a methane flux rate in terms of moles per year and ask whether that's most likely generated from an abiotic but habitable world model, or a biotic model, or an uninhabitable model. And they argue in this paper that this is most likely generated from a biotic model. Now, I don't want to comment on whether that's the right answer or not, but I think this is a very nice framework for building up different models and comparing an observation and asking which of these distributions is the observation most likely drawn from, where they argue that it's most likely drawn from a biotic example. But the thing to really recognize in any sort of framework like this is actually there's lots of assumptions that go into all of the different models that they've built. So to produce each of these distributions, they've had to use a model to simulate over lots of parameters in order to get a distribution. And in this case, those models include things like a model for geochemistry, a model for planetary circulation, a model of all of the biological and ecological processes. And so a lot goes into this, right? So this still fundamentally requires us to have theories for all of these things and to really trust those theories. And so I think if anyone has questions about these predictions or assessing, where these observations sit, it really will come in at the level of questioning the assumptions that go into producing these distributions. All right, and that's really important to understand, is that when we're trying to build a distribution, we require theoretical models to help us get a sense of generating, say, artificial data as they did here. A nice summary of all the different types of things that one would have to consider to build up all of these different probability distributions is again in this Walker et al. Paper. And so I would point people to that to sort of read and digest a lot of the different points they make about the different types of knowledge that you would need to gather to build up these different probability distributions. But the thing that I really want to point out here is that models really matter. And we still need theory in many cases to guide us because we're still asking questions about how different life could be, how different geochemistry could be. Those are still fundamental to assessing how likely an observation is to be a sign of life or not. And what I want to say is that often it's necessary to radically change assumptions about what the world looks like. And often observations can point us to doing that if we have a good theoretical basis. And so one of the most famous examples of this, and one of my favorite examples of changing assumptions, is this whole idea of ether. So there is a theory of light propagation for a long time that assumed that there was a medium in the universe called ether, and that is what light was able to propagate on as a wave. And so the idea was that this sort of permeated the universe, and it's how light is able to move. And people then started thinking of ways to test for this existence of ether. And one of the ideas is that if it was this background medium, then the relative motion of the Earth through that medium, both as it rotates, both as the Earth rotates for a day and circles the Earth for a year, those relative motions should cause you to see slightly different speeds of light as you move through this stationary background ether. And the Michelson-Morley experiment used an interferometer that had these perpendicular arms to test whether light had different speeds along those two arms at lots of different positions and at different times of day and different times in the year, where the expectation is as you moved those two perpendicular arms and you did both daily and annual experiments, you would be able to see variations in the speed of light. They were very careful about calculating how big an effect size that should be, given what they knew about the speed of the Earth and the speed of light, and sort of taking a ratio of those two speeds. And then this is known as sort of the most famous negative experiment, because they found no evidence that there was this a change in the speed of light based on all of these different positional experiments in this interferometer. And so this really started to call into question this idea of ether. And this is one of the sort of lines of support that allowed people to accept these theoretical ideas that Einstein produced around special and general relativity, where the assumption then changes to this simple but sort of bizarre idea that you have a constant speed of light in every inertial reference frame, and all observers seeing light independent of what inertial reference frame they're in will see light move at a constant speed. That, as we all know, has very bizarre consequences for time and length dilations. And then when this was generalized to general relativity, the addition of thinking of gravity as curvature was another assumption that was made. And although these have very bizarre consequences, these assumptions, they also lead to a really nice testable set of predictions. One is that light should bend around large, massive objects, such as the sun. And so this led to the proposal of this eclipse experiment, where the idea was you could look at a star field and then wait for the sun to move in front of it and watch the relative position of stars change dependent on how far away from the sun they were. And you need an eclipse so that the sun is not too bright an object to observe. And what's interesting was this comes along from the theory with a very specific prediction, which is that the change in theta, the angle between two stars, should be this simple formula that's based on the gravitational constant, the mass of the sun, the speed of light squared, and then the radius between the center of the sun and the observed star that you're looking at. And so this makes an explicit sort of a priori prediction that one can test. This is something that's happened lots of cases in physics, where ahead of time people know exactly the effect that one would expect and the effect sizes and how to look for it. And now for life, we're dealing with a much harder problem, because we have this very high dimensional space, potentially. Just looking at life on Earth, we see a vast diversity of organisms. And we understand that there may be sort of many ways for life to originate, with many diverse evolutionary trajectories after that. And yet, if we're trying to build models for detection, I think we really do need to continue to push theory far forward. Even for something like a Bayesian inference, at some level, that's going to require us to make assumptions about life in those models. And so we really do need a universal theory of life. And I would say that despite all of this diversity on Earth, I think there is hope for such theories. And so here's one example where if you take huge amounts of diversity, but you sort of zoom out and you look at the logarithm of mass against the logarithm of growth rate, in this case, plotted as a biomass production rate per individual per year, you can see these systematic scaling relationships that transcend huge amounts of living diversity, going from unicellular organisms all the way up to large multicellular organisms. And while there's a lot of variation in these plots, there is a central tendency, and we can often write down theories that predict that central tendency and then ask questions about how universal that theory is. And so recently, we've taken bacteria and started to do things like systematize different aspects of physiology, like how much DNA content a cell has as a function of cell volume. And you can do this then for all of the macromolecules in the cell, and then make simple predictions for how things like stoichiometric ratios, say nitrogen to phosphorus, will change as a function of cell size. And what we find is that you get these complicated but constantly changing relationships between cell size and stoichiometric ratios. The dashed line on this curve is the Redfield ratio for people who know a lot about that. And one can start to then use this to build different sorts of biosignatures that we think are based on fairly general physiology. And I won't go into the details of all the different ways that we generalize this in this one paper, but it does start to go from things that we know about extant life to generalizations that might allow us to make predictions for life anywhere. Now, there's a huge amount of work still to be done there. But I think this is the type of thing we need to do to inform what sorts of detection limits we might have, and to start competing different models against each other, given sets of data, perhaps in a Bayesian framework. So looking forward, I think we do need lots of new types of predictive and general theories for life. And I want to encourage people to continue to think about these advanced statistical frameworks. I think using Bayesian inference as a guide is a great idea. One just has to be careful in thinking through the assumptions they're making in the models they put into that, and understand that those assumptions have consequences for the answer. And I'll just say that in general, statistical inference is now a field of itself. I know lots of people who most of their life is thinking about new methods for different types of statistical inference. And these methods have been deployed across a huge range of disciplines, from public health and epidemiology to problems in computer science, machine learning, bioinformatics, archaeology, quantitative sociology, climatology. And so there really are a huge number of experts out there who have grappled with very hard problems of inference and model competition. And so in the spirit of this standard of evidence, I would just encourage people to continually reach out to some of these experts in statistical inference to help with various problems, and to ask sort of where is the frontier of statistical inference methods, because it may be useful in lots of contexts. So thank you for your time, and have a nice day.